Good afternoon. We'll start a afternoon session. And first talk is given by Po Chung Chen, local here, and he's going to talk about quantum critical spin 2 chain with the emergent SU3 symmetry. Let's welcome him.
Good afternoon, everybody. I would like to thank organizer for inviting me to give this presentation. So today I'm going to talk about our work in this quantum critical spin 2 chain with emergent SU3 symmetry. And first, I would like to thank my collaborators, including my former student, Ian in Australia, Min Chang in Zhongxin University, Miguel here, and also Sankit and LP as academic syndicat. And so there are basically three related references. So first, one is PIO this year, and there's a PRA in 2012, and also a JSD Mac paper. Okay, so the motivation of this work is to try to study the quantum mechanism in coherent system. So we want to see if there are more complicated mechanisms that can be simulated by a coherent system. So then we think about what are possibilities. So basically, we are interested in either. So there are many ways. So you can go to a higher spin with SU2 system, or you can try to implement an SU and Hamiltonian with coherent systems. Okay. So in this work, I'm going to concentrate on SU2 and a spin 2 system. So supposedly you have a spin 2 boson, and because we are going to use a DMRG, so we're limited. We want to concentrate on 1D lattice. So in this case, if you consider spin 2 boson, and then also you consider the case that is basically one particle per side, and then you can write your Hamiltonian in terms of projection operators. Okay. And those coefficients epsilon 0, epsilon 2, and epsilon 4 are related to the scaling length of your boson. But computationally, this is not the most straightforward basis to work on. But you can show that you can convert this projection operator into a spin 2 operator. Okay, so this coefficient will be depend on your epsilon, and then your coupling will, because we have spin 2, so you can have this S dot Si plus 1 can be from 1 to 4. So this Hamiltonian has a full SU2 symmetry, so we never break the SU2 symmetry. Okay. And for this reason, we are going to use the non-abelian DMRG, which in this non-abelian DMRG, we keep the SU2 symmetry explicitly. Okay. So it's conventional DMRG doesn't preserve SU2 symmetry, but in this, we basically preserve the SU2 symmetry. Okay. So first, we show the phase diagram we obtained. So this will be in 2012. Okay, so you can get the mean field diagram. So I want to explain this triangle first. So these three numbers are basically epsilon 0, epsilon 2, and epsilon 4. Okay, so basically you have this, and you have overall normalization factor. So these three tips. So this is basically the Hamiltonian is -1 projection to the 0 total spin space. And this is a project to a spin 2, and this is project to a spin 4. And remember, there's a minus in front of my epsilon. Okay. So if you want to project to a two spin project to a spin 4 space, basically you can think about this. You will form a ferromagnetic state. So first, Sankit has calculated this mean field diagram before. So basically, you have in the mean field level, you have ferromagnetic phase, you have a so-called cyclic phase, and then you have a polar phase. And then first we use the DMRG to calculate the phase diagram. Okay. And then we find that basically the phase boundary will shift a little bit, will fall on different line. So this red dot means the phase boundary obtained by DMRG. Okay. And if you plug in the scalar length of those material, so we find interesting. Okay, so in the DMRG, so we find the ferromagnet is still a ferromagnetic state, and this polar phase become a dimerized phase. So in this dimerized phase, if you look at the SI plus 1 correlation, you will see a kind of up down kind of pattern. So because this is the system is dimerized. And if you look at here, if you look at the same correlation function, you'll find it have a kind of period 3 pattern. So it has like weak, strong, weak, strong. So it has kind of period 3, like 3-side structure. So in the beginning, we call this kind of a trimerized pattern. So here the system is trimerized. Here the system is dimerized. And if you plug in the scattering length of those material, then you find, unfortunately, all of them are kind of close to the phase boundary. So if you want to do an experiment, it's probably hard to see they are actually in any phases. So since it is already, so we want to propose some experimental way to do the experiment to see if it's in the trimer or dimerized phases. So the way we propose is basically you can impose the superlatives. Okay? So the idea is like simple. So if supposedly your ground state is dimerized phase, but somehow I artificially impose a period 3 structure. Okay, and when so I sort of force the system to be trimerized. So when at the end, so the system will become trimerized. But you know the system originally, suppose the ground state is dimerized. That means there must be a phase transition. So the gap must go to 0. So if you impose superlatives with different strengths and see if the system goes through some particular phase transition, then you can sort of determine the original ground state is dimerized or trimerized. Okay. So that's sort of explained in this figure. So like for sodium 23, if you look at in the phase diagram, it should be a dimerized phase. Okay. So if we put in here the lambda 3 means like how you weaken the bond at every 3 sides. Okay, so if you go to 3, basically you enforce a trimerized pattern, so the system has to be trimerized. So if you trace the gap, so if you impose the dimerized superlative is compatible with your order parameter, so the gap is still there. So you can trace the gap, and here you see that somewhere it goes through a phase transition. Okay. And if you look at this point, it should be trimerized. Okay, so if you kind of impose a dimerized superlative, at some point it become the gap goes to 0. But these open symbol are like finite size calculations. If you extrapolate to infinite size the gap, here for this dimerized here, you see the dimerized phase is gap. Okay. Somehow if you do the same explanation for the trimerized phase with a 3-side superlatives, but you have a finite strength of superlative, you see it's gap. But somehow if you don't have any superlative, it seems to be that the gap is go to 0. Okay. So that means that here, if we don't have any superlatives, then maybe this so-called trimerized phase actually gapless in the thermodynamic limit. Okay. So for this, you can do a kind of 1/n scaling for your gap. Okay. And then so you can with different superlatives. Okay. So from this figure, basically we can sort of show that suggest that for this trimerized phase, actually it's gapless in the thermodynamic limit. So then the natural question to ask is what is the critical theory for this gapless phase? So basically we want to identify the conformal theory describing this critical period 3 phase. So now a typical way is to identify the central charge and scaling dimension of this CFD. And the popular way nowadays is to do entanglement entropy scaling. Okay? And for this, you can do finite size and infinite size. And more like a sort of traditional ways is to do finite size scaling of ground state energy and excited state energy. So for entanglement scaling, entropy is like you have a system and you put a color system into A and B, you trace out a B, and you can get reduced into the A. And if the system entanglementally, the system have conformal invariance, then you can show that for periodical system and you can have this scaling. So this big L is the system size. Small l is the size of your system A. And if you go to an infinite system, but like you slightly off critical with some correlation length, and then basically you replace this both boundary scaling by L is replaced by this correlation length. So if you do, for example, you do some kind of Heisenberg model, and you do finite size entanglement, you can get this curve. Okay, basically it's from this formula. And if you fill this formula, you can get a central charge. Okay, so that's kind of a very standard way nowadays. So we try this on, and also if you do infinite, then you get a straight line. This is log correlation. This is entanglement entropy. On slope, you can get the central charge. Okay, so we basically use this method doing finite size calculation. Okay, and then we get a very strange result. So basically, if you fit this formula, the C we get depend on. So there will be two parameters. One is your system size. One is your how many DMRG state you keep. Okay, so the number of central charge we get is from 1.5 to 3 something. So it's very strange. It didn't seem to converge to any value. And I want to remind you that so we are doing actually a SU2 calculation. So we keep like 2,800 SU2 bases. So effectively, that's like a 25,000 normal DMRG bases. So this is already quite large calculation in terms of DMRG. And we go to up to like L equal to 120. This C doesn't seem to converge. Okay. So somehow this doesn't work. So we want to go back to the energy finite size scaling. So the method. So we want to do first, we do some exact diagonalization. Okay, so we do this and we see this low energy excitation spectrum. So we see an interesting like basically a period 3 pattern. Okay, and then we can see what's the speed of the excitation here. So this period 3 kind of lead us to see that maybe what are the possible kind of CFT. Okay, so we find if the lattice size is multiple of 3, then the ground state is a singlet, and then so you have SOMO at 2 power 3. So that makes you wonder maybe this has some kind of approximate SU3 symmetry. And then you can list like sort of possible CFT and their corresponding central charge. Okay, so we see this range like basically this SU3 level 1 and maybe SU2. SU3 level 1 is kind of one of the possible CFT for this method. So how do we see if it actually is a SU3 level 1 to describe this? Okay. So but to do this, we sort of go back to the spin 1 bilinear biquadratic model, because here it's known that when J1 is equal to J2, the system has exact SU2 symmetry, and there's the extended SU2. A critical period 3 phase, which is described by SU3 level 1 WZW model. So we want to learn some lessons from this model. Okay. So basically, we do the same thing. We do the exact diagonalization for this spin 1 model, which is simpler. Then we can see a similar kind of period 3 pattern, and also we can match what's the spin here. Okay. So for here, we basically see the soft mode, like because it's split into in the SU3 range is 3 cross 3 bar. So in SU2 become 1 and plus A. So this becomes x equal to 0 and x equal to 1 and x equal to 2. Okay, so here you can see this 0 and 1 and 2. Okay, and which is also the same for our spin 2. So that kind of gives us more confidence that maybe this spin 2 model, at the critical period 3 phase, the CFT is actually SU3 level 1 WZW model. So to have more definite answer, like we we want to check this. Basically, we want to check if the central charge is equal to 2 and the scaling dimension is 2/3. But as I mentioned before, using entanglement entropy scaling to fit this central charge C doesn't work very well. Okay? So now we go back to this kind of finite size scaling of ground state excited state energy. From the ground state energy scaling, you can get a central charge C. Okay? But here we also have to fit the spin wave velocity numerically. And then by the excited state, finite size correctly excited state energy, we can get a scaling dimension. But there will be this log correction somehow, which will be sleeping because our system only has SU2 symmetry. But we can use this some rule to at least to the first order, leading order, we can cancel this log correction. Okay, so that we can still see a pretty good this 1/L scaling for the scaling dimension. Okay, so if you do. You plot this, and then you plot the ground state energy as function 1/L squared, and this is fitting for the spin wave velocity, and then you can fit the scaling dimension. The answer we get is 2.11 and this 0.628, which is kind of consistent with the prediction of SU3 level 1 WDW model. Okay, so our phase diagram sort of you can think about compared to this spin 1 bilinear pi quadron model, which also have a ferromagnetic phase, a dimerized phase, and a critical period switch phase. So in our spin 2 model, we also have ferromagnetic phase, dimerized phase, and the trimer, and the critical period switch phase. Okay. So to summary, basically we studied the spin 2 boson in 1D optical lattice, which has a SU2 symmetric Hamiltonian. It has the ferro, trimer, and dimer phases, and the system is gapped. For this trimer phase, the system is gapped for finite lattice, but it's gapless, critical period 3 at infinite zero. And for this infinite lattice, we're trying to identify the critical theory. And by using ground state energy, excited energy finite size scaling, we find the SU3 level 1 WZW model. So the system will actually have an emerging SU3 symmetry at the infinite, at the thermodynamic limits. Thank you. Yeah.
What are the leading irrelevant operators at this SU3 symmetric point? Current?
In spin 1 bilinear pi quadron.
No, in your spin 2 model.
In your spin 2 model.
So there must be SU3. Level 1 has SU3 cross SU3 symmetry, has a lot of symmetry.
Yes.
It's not present microscopically, so there must be many terms that I guess are irrelevant that violate it.
Yeah,
so to understand the nature of the correction, you would think you would need to know that. Is it understood for the spin 1 bilinear biquadratic law?
For spin 1, yes. For spin 1 bilinear quadron, I think it is understood.
And what's the answer? Is it current?
Yeah.
Couplings, or is it?
I think it's good. I'm not 100% sure. Misunderstood the time somehow. Sorry. Yeah, sure. I need to use another.
Ooh, cool. So right at the very beginning, you were showing a couple of ways to try to determine C by entanglement entropy.
Yeah.
So one of them was with infinite.
Yes.
How do you do that? So if it's
so that's
what are you scaling with for the infinite system? I mean, because the entanglement must be infinite for.
So for infinite system, you scale with the correlation length.
And how do you tune?
So this is kind of numerical trick. So in any DBM, in any numerical calculation, your correlation length is finite.
Yeah, but is it, you're tuning that by the number of states in
Yes,
the DMRG?
Yeah, but it's kind of indirectly.
Yeah, so how do you know the correlation length through the scale?
Okay, simple. So, well, straightforward. So, I don't have figures. So basically, if you have a DMRG state, you can diagonal transfer matrix, and you can get a correlation length. So you increase the M, you increase the correlation length.
Okay.
You don't control it directly.
I see.
But it's always finite, so you can always plot this somehow. Yeah.